Magnetic fields. This is the first video about magnetic fields. Now, what is a magnetic field? A magnetic field is a region of space where, and there's a list of things which experience forces in a magnetic field. There's magnetic materials like iron, cobalt, nickel, other magnets, moving charges, and currents. They all experience forces in magnetic fields. We can represent a magnetic field by drawing magnetic field lines, such as around this permanent magnet. So these imaginary lines in space, and how close they are together tells us what the strength of the field is. And magnetic field strength, we use the symbol capital B for magnetic field strength. The direction of the field is the direction of the force that would act on a north pole. So if you imagine I put a little north pole somewhere in that field, what would be the direction of the force on it? Magnetic field strength, we've said, has the symbol capital B, and it is measured in Tesla, capital T, named after Nikola Tesla. Looking at these two magnets here, there's a north and a south. Imagine there's some stuff flowing from north to south. Imagine stuff flowing like water flowing. And this imaginary stuff, we call it flux. So flux flows from north to south. And my magnetic field lines, you can call them flux lines. And flux is a quantity. It has the symbol phi, and it is measured in Webers, WB. So there's an amount of flux flowing from north to south. Now, magnetic field strength is equal to flux density. In other words, the amount of flux that flows through a particular area is equal to the magnetic field strength. Magnetic field strength, B, equals phi over A, Webers per meter squared. B equals phi over A, a very important equation you should know. Okay, so the amount of flux that flows through a certain area tells me the field strength. A Weber per meter squared is equivalent to a Tesla. Currents produce magnetic fields. The diagram on the left, a long straight current carrying conductor produces a circular magnetic field. This was discovered by accident by a guy called Ørsted. The strength of the field depends on the distance. Obviously it gets weaker, and it depends on the current. A single wire isn't going to produce a very strong field. If we wrap our wire around a tube to make a coil, and we put a current through that, then we get a much stronger field. And the strength of the field inside the coil will depend on the current, the number of turns, how close together the turns are, and the material inside the core. It's permeability, the permeability of the material inside the core. I'll introduce a term now, flux linkage. Flux linkage just means that if you have a coil with n turns, then instead of just saying phi, you say n phi. N phi is the flux linkage. Basically multiply by the number of turns to get the flux linkage. This is very important. This is an analogy between an electrical circuit and a magnetic circuit. On the left-hand side is my electrical circuit. Now, in both circuits, we have something pushing. On the left, we've got voltage, EMF pushing, and it pushes the current, and the current flows, and the current flows through a conductor. And the conductance of the conductor lets us know how easy it is for the current to flow through. So V equals I over G. I mean, hopefully you remember V equals IR, and resistance and conductance are the opposite of each other. So V equals I over G. But more importantly, V is pushing, I is flowing, G is how easy it is to flow. Now on the right we have a magnetic circuit. What's doing the pushing in this circuit is current turns. You'll see that there's a coil at the top, And this coil, Ni, if you put a current in the coil, that produces flux, and it pushes flux around the magnetic circuit. So the thing pushing is Ni. The thing flowing, which is analogous to the current, is flux. And then how easy it is to flow through this particular core is called the permeance of the core. It has the symbol lambda, and it's analogous to conductance. Permeance is analogous to conductance. So lambda is a property of the core called its permeance. It's analogous to conductance. It depends on the dimensions of the core, and it depends on the permeability of the material that it's made from. These cores are usually made from iron because iron has a very high permeability. You get lots of lovely flux flowing through iron. By the way, a very common exam question, it will ask you just to draw 2 complete loops of flux in an iron core.